So, like I was telling you guys, the OSI model is more of a reference, a guideline to help us delegate responsibilities, to help us understand what the communication process entails. And so I had you guys just list them out from top to bottom. But remember, the communication process entails both directions. Going down the stack is what we call encapsulating, and going up the stack we call decapsulation. And today I hope to explain why the encapsulation process is very critical to the communication. That is, to get the message from the sender to the receiver. Layer 7, layer 6, and layer 5 can be grouped in. In fact, the sole responsibility for the three of these is to produce what for the transport layer? Yeah. So by the time we get down to the transport layer, the PDU should look something like this. It should be in a binary format. So these three layers produce a PDU that we will call data. PDU is short for what? Protocol Data Unit. Depending on the application, all the encryptions and the compressions, these zeros and ones are going to be something that's really trivial. I mean, that's what network people see all the time, are just zeros and ones. They don't know if it's an email, or it's a voice communication, or whether it's a video stream. In fact, that's what we call the converging network, right? The digital converging network. This is why Time Warner and all the other companies can offer you phone, internet, and TV all on the same line. It's all zeros and ones. Once you get into zeros and ones, you need to identify that. Typically, on the application layer, we identify zeros and ones by a file extension. A .exe represents zeros and ones used to execute instructions. A .jpg represents those zeros and ones to display a picture or color, right? Likewise, we have identifications used in networking. Sometimes we call these addresses to identify the application of the service. That's the first thing that the transport layer is going to do. The transport layer is going to identify what application's making the request and what service is going to receive this. Applications make requests. Services receive them. All right? So the way we identify them is through port addresses. There's going to be a source, and there's going to be a destination. We stamp each and every one of the PDU for the transport layer with the source and destination. What is the PDU called for the transport layer? Segment. And why is it called a segment? Because what is the second thing, or I should say, technically this would be the first thing. Yeah, it takes the data and it breaks it up into pieces, hence we call those pieces segments, right? So the PDU for the transport layer is called a segment. Why do we segment our data? Security, performance, and we can also allow multiple communications to occur relatively at the same time, which we call multiplexing, right? What was one of the protocols that defined the segment? Because remember, protocol data unit, right? So if we're producing a PDU, there's got to be a protocol that told me how to produce that PDU, correct? So what was one of the protocols? TCP was one of them, absolutely. In TCP, we said time's irrelevant. I'm going to sacrifice time over reliability. Okay? This is why those big fat Cadillacs have a bunch of luxury items in there that add weight to the car, but a sports car, which is going to cost more than a Cadillac, I mean, if you're getting like a high-end sports car, probably going to trim all that fat because they want speed, correct? So what was the other protocol designed? UDP. TCP is the most popular one. All right, we pass that segment down to the network layer. And what is that network layer going to produce? What are we going to take that segment and make it into? A packet. And what is one of the most popular protocols on this layer that tells the operating system how to take a segment and make it into a packet? IP. And with IP, we have a source and a destination address. Much, much bigger than port addresses, but nevertheless, same principle. But what's the difference between these addresses? What does the transport layer use addresses for? They're both logical, but which one does what does the transport layer use addresses for? To identify what? They're called port addresses, but what do they use to identify? Services or applications. Because look above the transport layer. The transport layer is looking up and says, okay, who's getting this data? Who's getting that data? The way they know that is through port addresses, okay? So what are the addresses used at the network layer? What are they used to identify? The key is network. What is the definition of a network? Two or more devices connected together, so they got to identify the devices on the network. So the sender and the receiver's IP address goes here into the packet. All right, so the packet gets passed down, and that becomes what? So we're in the data link layer, and we're going to produce what we call a frame. Remember, the frame is the only time we add a header and a trailer. And that frame uses, well, we could use all kinds of different protocols. I always like to talk the data link layer with the physical layer because its idea is to connect all that logical stuff. Now, the way I explained in my last class, and they got a kick out of it, but I think it clicked. Can you guys tell me what Internet Explorer smells like? I know you guys are going to say, well, it smells like shit because it's a piece of shit. But what about Firefox? What about Chrome? What do they smell like? What do they feel like? When you guys touch Internet Explorer, what does it feel like? Felt a little heavy, squishy. It doesn't have a smell. It doesn't have texture because it's all virtual. It's abstract, right? If I tell you what if I ask you what a 9-volt battery feels like, you guys can tell me, right? That's down here. The physical stuff is what we touch, what we work with. So this layer is to take that abstract stuff and make it into something real. And we need standards. We need standards that tell me, okay, I can work with all that logical stuff. Give me all those zeros and ones, and I'm going to convert it into something that people can touch, taste, hear, feel. See. All depends on your interface card. Now I say hear because if you could hear like my dog or beyond, you can hear the Wi-Fi network sending messages. And they operate at 2.4 gigahertz spectrum. That's well beyond our hearing, and you guys are going to be glad for that. I mean, the way we listen to FM radios, which are in the megahertz, is you need a tuner to tune into that frequency and then to tone it down to a range that you can hear, correct? Networks, we call them modems. But nevertheless, those signals are all over us. They're in this classroom all the time. I'm sending one from this microphone to my phone. It'd drive me nuts if you guys heard or saw all those things. But they do exist. The question is, how do I know that the interface card that I bought is going to work with my other devices on my network? There's got to be standards. Like when you go shopping for a hard drive, it says USB, or a flash drive, it says USB. You know you have a USB port and you expect it to work. So when you guys go shopping for interface cards or network devices, what are you looking for? When you guys go shopping for wireless cards or wireless routers, what do you look for? It says Wi-Fi maybe, but more importantly, it says 802.11 followed by a letter. So our latest one is 802.11 AC. In order to use all that bandwidth, to use that wireless router to its full potential, what kind of interface card are you going to need? An 802.11 AC interface card. So don't stop halfway and buy just a wireless router. Go the extra mile and buy the interface card that uses the full potential out of that wireless router. Clear about that? If I was setting up a wired network like we've been doing in Packet Tracer, you click on the computer, it says what for the interface card? Fast Ethernet. And that is a protocol or a standard that happens right here, the data link. Ethernet has source and destination addresses, but they're physical. That means the company that made that interface card burned an address into that card that you cannot change. We'll get more into the difference between physical and logical. All right. Physical just takes those bits and produces a signal to carry them. That's it. Now, I tell my students there are other models that explain the same process. Some are less elaborate as this. One of the most popular models that we use as a substitute to the OSI model is called the TCP/IP model. Anybody want to take a guess why it's called TCP/IP? Because the persons that developed the internet focused on two protocols and only two protocols, TCP/IP. They needed to make sure the data was reliable because back when it was called ARPANET, everything was very sensitive. It was all this research. There wasn't any like voice or video, any of that kind of crap. In fact, the reason why the internet was developed was because of a Cold War situation that we connected our missile silos. So when Washington, D.C. was attacked, we could still give the launch codes over in Alaska or Turkey or wherever. So we had to develop a very reliable network. So if a pathway gets disconnected, we have another way to get there, another route. And that's what IP says. So they said, you know what? We developed this thing. Let's create a model that shows a grand overview of how this behaves. And they said, in order to use our network, if you want to send a web page, you're going to need a web browser. And so they said, the first three layers are going to be accomplished under the application layer. So I just grouped the first three. In fact, when we looked at layer 7, 6, and 5, didn't I say that's all software stuff? OSI model is a little bit more thorough and said, you know what? I don't want a cryptographer writing the user interface for my web browser. And thank God for that, because if the cryptographer did do that, they would hide the OK button. It's a secret. Likewise, I wouldn't want a programmer who develops user interfaces to write the cryptography program, because they would say, oh, it's real easy. Password's password. Because their job is to make the application user-friendly. The cryptographer's job is to make it very unfriendly, so that when you see it, it doesn't make any sense. Very thorough. And so what I like to see is, does that happen over here? Absolutely. Consider there's like a division, and probably in that division, there are these departments, because they need to be accomplished. We do need session stuff. We do need presentation stuff. But TCP was like, that's all in the software, and that's what we're going to do. And it too will produce data. And it too is interconnected. And it's going to connect to the transport layer. And it too would produce segments. Because I don't care how you communicate, but eventually in your communication process, you're going to need to identify what you're talking about. The subject, right? You ever talk to somebody, then out of the blue they bring something up and you're like, we were just talking about Hell on Wheels. Why are you talking about the weather next week? What did it have anything to do with the topic, right? So in there, you're going to need some way to identify what application or what service you're talking with. So transport layer, all the same. Remember, these are the people that developed the internet. So their layer isn't going to be called the network layer, but rather they're going to call it the inter-network layer. And what does inter mean anyway? Inter. It's just abbreviated from interconnected. So just a bunch of networks connected together. Networks are networks, whether they're jumped together or not, they all need to behave the same way. And it too is going to produce a packet. All right, this is a very simple model. So it's going to take the last two and group them together. And they're going to call this the network access layer. And oh hell, does that cause problems. So far I have a 99% failure rate on my exam when I give a multiple choice question and I say, which layer on the OSI model is the same as the network access layer? And I will only give you one. It'll be like network layer, network transport and session, something like that. And students want to say this one. Network, network, it's got to be the same thing. And it's not. The key here is access. Going on to the network. We're talking about the physical stuff. So it takes both the data link and the physical stuff in here. And it too calls its PDU a frame. Now let me give you an example away from networks into hardware. Because I'm a hardware guy. I love reading hardware magazines. I love staying on latest edge with CPUs, GPUs, and all that stuff, especially the stuff with the phones. Like iPhone just released a new processor they call their motion processor. And I'm just like, oh, wow, just another processor. Great, what does it do? And so I'm looking at this, and I remember back in the 90s, you know, you get into little geek fights and say, oh, NVIDIA is better than ATI or some crap like that. And then somebody would say, well, no, ATI's got great processors, and their GPUs are excellent. They have more transistors, and they have more shaders and everything. And I'm like, oh, yeah, whip-de-doo. And just like you guys might be getting in pissing contests with about Xbox 360 versus the PlayStation 3. Oh, yeah, PlayStation 3 has a lot of muscle compared to the Xbox. But what drives us to these game consoles? Content. Likewise, I was so discouraged with ATI because they had shitty developers. The people that developed drivers didn't know what they were doing because ATI needed to save money, so they said, you know what, you're an engineer, you're also going to develop the driver. What is a software driver? It acts as a translator between the hardware and the operating system, right? If your translator isn't doing a good job in translating, you can find yourself in prison, right? Likewise, if your driver isn't using the hardware to its full potential, you wasted all your money on all that muscle, and what you have is a dumb jock that can't read. And so you paid him millions of dollars to play football, but he doesn't understand the game plan. And so now he's running to the opposite field goal or running to the opposite end zone. And you're like, well, you're big and strong, but you're pretty stupid. So I'm going to get rid of you. Don't bring out any teams, but I kept it loose. Likewise. So what happened is over here, NVIDIA decided to follow a model like this and said, we'll pay for engineers, and we'll also pay for software developers that do nothing but develop drivers. You need them, but they just have more levels, which might cost them more, but hopefully they produce a better product. Over here, the same process has to be done. The communication process has to happen. However, how we group them and organize or delegate responsibility is our business model.